Our next talk is called Elastic Distributed Deep Learning Training at Large-Scale On-Prem and Cloud Productions. And our speaker today is Yonggang Hu. Thank you.
Hi. Hello, everyone. Grab pizza before it's gone. Only one piece for me. Before I start, just a quick call. Quick question. How many of you have run distributed training before? Okay. Oh, okay. Good. Okay. Then there's a good topic for today. I'm from IBM. We're still building machines, and this is the one we just built recently. It's called Summit. It's the fastest supercomputer in the world, and it has 27,000 GPUs, V100 GPUs, and I was leading a team building software for that machine. But we're also doing something more fun. We're building platform, building computer engine to do something interesting. For example, this is Formula 1 racing, Red Bull racing team using our platform, doing a lot of simulation to design a car. Using computer to design a car, and also doing simulation to simulate the race so that they can have a winning formula. Right? Decide what's the strategy. Rainy days like today. You know, I am from Canada, from Toronto. I was looking for good weather, and this is what I got. And also, they have a lot of sensor on the car. And over there are a lot of time series, there are a lot of prediction, there's vibration data, there's sound data, there are also video data, so a lot of AI technology being used over there. So today I'm going to talk a little bit about deep learning and especially distributed training. And after that, I will introduce our new technology called elastic distributed training. So deep learning, I think you all know, require a lot of data. Actually, data help deep learning. And Julie have a diagram showing when you feed a lot of data to traditional model, it's a plateau and now it's getting better, but for deep learning, it's getting better and better. So this big data definitely helps, and also the engine also helps because you need to have both compute and the data to make it go faster. And in many cases, right now, the compute is even more important because getting big data and also good label data is very hard. So this is a statistics or diagram from OpenAI, showing the demand of a compute. And you can see there's a straight line, but it's not linear because it's a log scale. And talk about over the past few years, the compute demand increased by 300,000 times. And this is the speed of doubling every 3.5 months. Instead of like Moore's law doubling every 2 years, this is doubling every 3 months. And if you apply 2-year-old, you will only get the 7x increase, but here is a 300,000x increase. So computing power is very important. This is NVIDIA's device, Tesla V100. Just make a guess how much it costs. What's the price for this device, this car? Anybody from NVIDIA? How much it is? Wow. You must from NVIDIA, right? So it's quite expensive. It's a 10K, and it's the price of a car, right? And that car can last for 10 years, and that device probably will be obsolete in 2. And then we build the machines. IBM also build machine. This is IBM's GPU machine. is the price of Audi. I'm a Audi. I have Audi car for 15 years, but I don't have this version, this AA. I only have A4. Right? I cannot afford AA. So then NVIDIA also have like a machine with a lot of GPUs, 32 GPUs, and that's the price of a car I will never have. so that's a Lamborghini, and then they have this supercomputer. It's a price tag of $500 million, and actually, oops. What's going on?
No problem.
Oh, okay. That's a price actually similar to the price to build a Formula One racing car, half a billion dollars. So results very expensive. Need to make a good use. Workload also matters. This ResNet 50. It is almost become a toy model, right? And for ImageNet 1K, it takes 14 days to train on one GPU. And if you have a Lamborghini, that will be 29 hours. And if you're lucky to have this racing car, it can be done in minutes. But one thing I want to point out is, in this world, there are only two drivers can drive this racing car, and each person got paid $40 million per year. So then this is a motivation, one of the motivation for the top. Sure, we build a faster computer, but we also want to this car or computer super easy to drive. Can go very fast, but can also allow me to go grocery and send my kids to school and or tow my boat. Right? So ease of use is very important. And on the inference side, story is different, right? Inference, there are only forward propagation and make a prediction. There's no batch; it's one at a time, right? There's no backward power propagation, so the cost is much lower. Now that means if you run this inference one at a time on this GPU, that will be super inefficient. And the utilization for this $10,000 GPU will be less than 1%. So those are the things we need to worry. And then there's a lot of model, a lot of tuning runs, a lot of big data set, a lot of parameters. So we want to make it fast, right? So if we make it fast, then what you can do, right? Sure, you want to have better accuracy, you want to build more model, and then that's all good, right? Or you have time to have more pizza. And if you look at the bottom, you will see the compute power increase and the memory increase and the communication, the bandwidth increase is not at the same ratio. Over the past few years, actually compute increased quite a bit, but not so much for the network bandwidth. So this is one of the problems we need to solve for distributed deep learning training. A little bit on deep learning training, there are pretty much two approaches. One is called the model parallelism. We essentially break the big model into smaller pieces, and then run those small pieces of model on different devices. Another one is data parallel. Data parallel essentially run the same model on one GPU or multiple GPU on one machine, and then feed different chunks of the data. And for data parallel, actually you will expect a constant traffic per GPU. Well, for model parallel, that's become a little bit tricky because this partition dictates the traffic, and it's not easy to design a very efficient model parallel. You can see it's easier to get a degradation when you have a more GPU for model parallel. So today we're gonna focus on data power. So this is an old picture, but for the newer model, this correlation still hold. Essentially, this is about the accuracy versus the complexity of the model. This is called a deep neural network. There's a reason there's a lot of layers. The mall parameter for the model, this model tends to perform better. And also, this is you can see the size, right? The size will also impact the communication, right? Take this BGG as an example. They have 120. It has 120 million parameters. And if we do distributed gradient design, then we need to do a synchronization or reduce operation every iteration. That's pretty much a gigabyte data need to transfer for every 4 GPU. So we need to think about how to do the communication. And each iteration actually is very short. It could be in tens of milliseconds or 100 milliseconds. So there's a simple approach. A simple approach is a parameter server approach. Is the one on the left side. Right, essentially different model on GPU working on different chunk of the data, and then you have a gradient on each GPU communicate with parameter server. Parameter server do an average, and then send back to all the different worker, and then update the model. So you can see. You can easily see there could be performance issue, and the parameter server could become a bottleneck. And once you put multiple parameter server over there is also a dilemma, right? How many parameters server you need to put over there? And if you put too many, there's all-to-all communication, not very efficient. So right now, for efficient distributed training, it's all use all reduce approach at the bottom. Right. For example, using MPI or NICO. Let's look at one example. This is a ring-based reduce, and also being used by Baidu's distributed training. Essentially, it had two paths. The first pass in n-1 steps. It will have a slice of the data, and then do the sum and aggregate on one of the worker. And then after that, for the next n-1 steps, we can do a broadcast so that all the GPU will have the same sum, same average. So problem for this one is. By the way, this is quite efficient, right? And it is quite optimal, but it suffers some problem. One is there's many iterations, and also when you have your topology is not symmetrical, right? When you have a weaker link in the topology, when you do the ring, and this communication speed will be subject to the weakest link, the lowest speed. And then over the past 1 or 2 years, there's other algorithm. For example, Uber and Tencent have this two-stage or hierarchical approach, and you can do the ring base on the local node, and then to do all reduce and broadcast at the cross node level. And it has some problems as well. There's still many iteration, and also the traffic pattern depend on the topology. So IBM also have algorithm and quite advanced algorithm. I don't want to go into details because I want to cover other part. There's a paper available. This is a NIPS paper the year before. And last December, we also have a further enhancement by leveraging compression, gradient compression. And over there, we want to solve a low bandwidth problem. What if you don't have infinite band? You don't have a 100 gigabit network. You only have 1 gigabit or 10 gigabit network, and how to do the distributed gradient descent. And we use approach. We use a matrix factorization approach to do that. There's the details, and there's a paper on that. And if you're interested in this is last December's Murex paper. So this is the main thing I want to talk about. So you have a high performance. You want to have a better scalability, but there are other things you need to consider. One is it needs to be flexible, and also you need to use multiple frameworks. There's TensorFlow, Pytorch, different things. We need to support different frameworks, and we also want to support developer transparency. Later I will cover that, right? Nobody wants to write more code. And auto-scaling elasticity is a key thing for today, and fault tolerance, service quality. And the last bullet is also very important. You don't want to lose accuracy. Right? You want to reproducibility, right? You don't want, sure, my model running faster, but I don't have accuracy. So let's look at elastic training. So I was visiting a lot of customers, and this is one of the top AI research institute. Over there, they said distributed training is great, but we only run training on one GPU. And I was with a group of people, students and researchers in the room, and I asked, you don't want to speed up? And they said, we are not Google, right? We only have 300 GPU, and we have 300 students, and each researcher only entitled to 1 GPU. And I said, you are all meeting here, in meeting room right now, and are you using the GPU that allocate to you? And they said no. But they also counteract, right? The smart students saying, if I ask for 16 GPU, and in a busy cluster, I will never get it. And this is a classic, big job starvation problems. And then they also said that if you run a big job, use more GPU than you deserve, later on somebody gonna kill your job. Your manager say, bad guy. I'm gonna kick off your job. And they said, what if you start with 1 GPU? One cluster is idle, you have a free GPU, and then you can grow. And then once other people coming in with other jobs, and you can gracefully shrink back to the GPU you deserve. And they said something like that. Right. So this is a great. This is a great about the distributed training. Let's look at the developer side. For developer, everybody wants simple, right? However, running distributed training is not simple. In the older version of TensorFlow, it's quite complex, and in the newer version of TensorFlow 2.0, it's getting a little bit better. And Harvard also made some improvement. There's 4 or 5 function calls, initialization. You add their wrapper of optimizer and then broadcast, right? Harvard making a little bit better, but they are all using MPI, right? MPI has a problem that I will talk about later. So in the distributed TensorFlow, there's a code not supposed for you to read, right? It mainly show you this complex. You don't want to do the beginning part, which is cluster setup, or the configuration, or starting hub, or starting worker. All those things are not good because this is essentially coupling the model with underlying hardware and infrastructure. It's not good for portability. It's not good for you move your code from development environment to production cluster. And sometimes the training loop also tedious, and those other things can also be simplified. So what we want is model developers should only focus on the middle section, which is the model development, and then that the platform and framework will take care of other things. Let's look at a little bit of MPI. MPI is still the fastest communication frameworks. At IBM, our team also building MPI, and our MPI also have maybe the best performance. Here we talk about 1 microsecond latency. However, MPI have a problem. MPI's problem is it's not elastic, it's monolithic, it's not fault tolerant, and if you have one rank crashed, and you lose the entire job. And that's not good because the deep learning jobs could run for weeks, and sometimes also hard to debug. So MPI's approach is essentially linking the communication library into the application code, and then you run the same code across multiple GPU machine, and the entire application is kind of monolithic. It's linking the communication library to the program. However, there is an alternative paradigm. Our alternative paradigm is client server, is decoupling, is the approach being used by, say, MapReduce or Spark, and also we build some tools as well. We don't want application developer link monolithic, non-tolerant, fault-tolerant library to the program. Instead, we want to end user to describe what code being executed at the server side and what code is being executed at the driver side, so that the scheduler and framework to take care of all the distribution and the task and the state and the communication. And by doing that, the end user don't need to worry about the workload management and the distribution. And you also gain the elasticity, resilience, and the mobility. So this is what we have done, right? We want the best performance and scale, flexibility, auto scaling, and we also want to give user prioritization. They can control high priority, low priority, apply scheduling policy and fair share, and support different framework, and also with a hyperparameter awareness. With hyperparameter awareness also super important. When you run multiple GPU and you think about learning rate and batch size and all those things. So this is a simple example. So the first job starts using a GPU at T0 to T1, and then the second job comes in at T1. And what you can see here is the fair share policy kicked in, and the second job get half of the GPU. And then the first job is just gracefully reduce the GPU to 4, but continue running. And then at T2, the end user saying, "I want to make the second job run faster, just increase the priority," and then the second job get one more GPU. And once the first job finished, and the second job get all the GPU. So this is a elastic distributed training, and also with a graceful grow and shrink. So how we did that? We have different layers. At the bottom, we have a communication library, more fault tolerant. We support different frameworks: TensorFlow, Caffe, Pytorch, Caffe, and we also have wrapper to provide the transparency. And then we have a driver. This driver very key. And this driver essentially just figure out how to run the training run, right? How to run the different batches on GPU, determine how to do the data ingest, figure out the plan, and also synchronization after every iteration. And then on top, there's a scheduling policy, and there's a resource allocation. So this is another. There's some diagram showing how this training run being executed, right? And you can see this is over the time how many tasks completed, and the line has a different slope, meaning that the rate of task finish rate is different because user have changing the priority or have a different job completing. From a user interface perspective, it's super simple to use. You download the model from internet, and this is a Keras, and it's the same model definition. On the left-hand side, this is how you run on single GPU, and then this is how you run through this elastic distributed training. Essentially, it's a one-line change, and it's a wrapper. It's still you're passing the model, the same loss, same optimizer, and the batch size, iPod, and then just run. So you have your code running successfully on one GPU, and then you take over the cluster, it just transparently run on multiple GPU. Same thing for Pytorch. And then the visualization, you want to see the progress, and we have a built-in logger, and so that later on you can see the accuracy, the loss, the histogram of the weight at the different layer, things like that. And I said earlier, auto scaling is cool, but the accuracy also very important. When I present to the research institute, they said, oh, how about the reproducibility? I need to publish a paper. I don't want a different result if you use one GPU versus 4 GPU. And we guarantee that, we guarantee the same accuracy curve. Quickly show some performance benchmark, pretty good, 90+ percentage efficiency, and also when you run multiple jobs in a multi-tenant environment, and the overhead is very low. So probably very soon we'll publish some bigger scale result. We run on a few thousand GPU, and I cannot disclose right now, so just wait. And this is essentially a very simple scenario, just showing why elastic training provides better efficiency. And here, if you have a 4 job, each requires 3 GPU, and if you run on a 4 GPU machine, and you will have 1 GPU not being used. However, if you have elastic training, if you can grow and shrink based on the capacity and the contention, your GPU always fully utilized. We building platform, and the elastic training is one of the platform, and then we also have inference, hyperparameter tuning, and other components. IBM have user interface, we have Studio, we have pipeline management, What'sML, and also What'sML Accelerator. Those are the capability, and elastic distributed training is a part of Watson machine learning Accelerator. There's more reference at the back, and I think slide can be published, and I will stop here. Any question?
Thanks very much. Could you go into more detail about preemption? I think you mentioned that on.
Okay. So this is essentially a production scenario. This is essentially a production scenario. The first job starts with a GPU, and then the second job kick in, and the second job, because it's fair share and equal priority, the second job deserve 4, and the second job will get 4. And the first job will gracefully release the 4 GPU. So we, the first job release at GPU, the way we release is at the iteration boundary, and the scheduler working with the driver, and will notify the driver saying you need to release a 4 GPU, and then the driver after finish this 4 synchronization or reduce synchronization, and then will give up 4 GPU. And then the next iteration need to think about how to index data, how to dispatch the mini batch, right? Because before you use a GPU, right now it's only have 4 GPU. So there's some adjustment that needs to be done over there, and also make sure you know the batch size, effective batch size needs to maintain.
Thank you for presentation. Could you share half of GPU or preempt here?
Okay, that's a good question. Actually, we're working on that. We already have one version released to our customer, and the motivation for that is we found out sometimes for the model training, especially in banking, when they run the time series data, and you actually cannot occupy entire GPU, fully utilize the entire GPU. And you don't want your very expensive GPU being idle. And in that case, you will need to pack multiple models on the same GPU. And this is also useful for hyperparameter tuning, right? Hyperparameter tuning, you could run multiple small experiments on the same GPU, right? So over there, because we control, we know how long the iteration take, and memory size and the calculation, we actually can have a control to at the sub GPU level, say half of GPU or 40% of GPU. So we released one version, is more static, and we are working on a smart, packing and smart GPU preemption at the sub GPU level. Yeah, thank you. Yeah, good question.
All right, let's thank our speaker again.
Thank you.